All right, so the target for today is to do 11.1 and like wrap it up, okay? So ওইটা হয়ে গেলে 11.2 যেটা ওটা তোমাদের সামনে আমি নেক্সট ক্লাসে শেষ করে ফেলবো and we'll be done with the syllabus. 11.2 is a very odd topic, right? So it's better if we have a discussion on it as we do the topic. So তার জন্য ওইটা হচ্ছে I'll keep it for next class, which is on Tuesday, okay? But আজকে whatever time it takes, আমাদেরকে হচ্ছে 11.1 শেষ করতে হবে. I feel like 6 o'clock মধ্যে definitely হয়ে যাওয়া উচিত, but extra time নিয়ে রাখছি, মানে I think it should be done much earlier than that. Anyway, so I talked about this before, and এখানে essentially যেটা করতে হবে, we need to address two things. একটা হচ্ছে the process of finding the structure of an atom, which is basically the core of this chapter, and also we need to look into the idea behind your different particles that are emitted, like alpha, beta, gamma, or their properties and whatnot, right? So that's mainly the chapter. So শুরু করি। আমি পুরো জিনিসটা স্ক্র্যাচ থেকে বুঝাবো। এখানে মোটামুটি সবকিছু নোটস দেওয়া আছে, সো জাস্ট শুনলেই তোমাদের এনাফ হবে। And on top of that, you have done this in your O levels, okay? So তার জন্য it's not like you're going to be looking into something new. The thing that's new, that's 11.2, যেটা আমি তোমাদেরকে upfront next ক্লাসে দেখাবো। Do you guys have classes from 5 to 6? Or you can be here till 6? 5 to 6 classes or? Achha, okay. আমি হচ্ছে right. Problem is my laptop is out of space and record korte dicche na. Let me see that. Just give me a minute. Let me delete some of the previous stuff we have. Okay.
Recording in progress.
You guys have to leave with it. You can go from the line. All right, let's start. So what's going on here? What's the chapter dealing with? So it's the structure of an atom. Okay, so this is atomic structure. So what's the structure of an atom, and how do we figure that out? So there's a backstory here. If you part of it, not all of it. So backstory it is the evolution of an atom. Okay, so what's the evolution of an atom? Okay, so basically we come to know what the atom is until a bit recently, until we had some assumptions out there. All right, and what happened here is that the original structure of an atom was considered to be just single particles like that, right? It's called the John Dalton model. Something Dalton model. তারপরে হচ্ছে we have the J.J. Thomson model, and তারপরে we have the Rutherford model. এই মডেলগুলো আমাদের জানতে হবে, okay? So the the Dalton model basically told you that atoms were indivisible. Okay, so they're like made up of these small units, যেটার নাম coined করা হয়েছিল by him. He called them the atom, and he said that this is the thing that was wrong about his prediction. He said that these were indivisible. So he said that atoms can't be divided any further, right? And they're the smallest units out there. He also said that these atoms, right, they have like a mechanism to latch onto each other. And the mechanism works like hooks, and the size and the shape of the hook needs to be appropriate in order for them to, interact and stick together. And that eventually is what we now know as the bonding mechanism. So this is what we refer as the chemical bond. So John Dalton was wrong in giving us a picture of the atom, but he was actually the first person to suggest that there are chemical bonds out there, and that the bonds are unique to every element. That's why not everything reacts or interacts with everything else, right? So that's what chemical bonds are. This is the Dalton's model. Okay, so Dalton's atomic structure, right? Then what happened was this was just there for years. It wasn't really advanced, so কিছু এটাতে করা যায় নাই. Then until 1900s এর শুরুর দিকে, right, they discovered a lot of things suddenly. So they suddenly figured out that there is something called the electron, and then they figured out there's something called the proton, and these are smaller than the atom, right? So now we know that the atom can further be broken down, right? And what would the shape be? So তখন যেটা করছে this person, J.J. Thomson, right? He came up with this idea for the structure of an atom. He said that the atom was this semi-permeable material. Okay, so permeable meaning that things can go through it. Okay, so think of it like a jelly-like material. So this is permeable. And he said that this jelly-like material that is out there is actually what the proton is. So that's the proton. And he said that the proton is positively charged. So that's a big positive charge out there. And he said that the electrons, right, are actually scattered within this jelly-like material. So this is your proton. And the electrons are scattered within this material. So like, there are like electrons at different locations of it, like that. And these are obviously smaller. So we know that electrons are like almost 2,000 times lighter than the proton. So this is what the electrons were. And this was called the J.J. Thomson model, but we don't call it J.J. Thomson model. There's a different name for it. Do you know what the name was for this particular model, where the core structure was positive proton and the electrons were like floating inside it or suspended inside it? Does anyone recall the name of this model? Very good. It's called the Pi model. No, Pi not. Plum pudding model. Okay, plum pudding model. So the plum pudding model is based on the assumption that it's like a pudding. Plum pudding টা হচ্ছে কিরকম দেখতে? কেন এই ওয়ার্ডটা ইউজ করা হয়? So just think of what can I give an example? Fruitcake. Fruitcake is a very good example. So imagine you have this fruitcake here. That's the proton. And fruitcake ভিতরে you have pieces of fruits, right? So you have like, raisins and stuff like that. So এটা হচ্ছে ভিতরে different জায়গায় scattered করা, right? So these are like pieces of fruit inside your fruitcake. So that's the model he said. Okay, that's the J.J. Thomson model. Plum pudding was his version because তখন plum pudding is তখনও না, এখনো it's like a popular dessert. But on the reference in general, you think of the bread, the dough, as the proton, and inside the proton, right, you have your electrons scattered inside it, right? So those are the electrons. And he said that the protons and electrons have same charge, right? Same charge as like, amount is same. So the net charge of your atom is going to be 0, so neutral. So it's called a plum pudding model. And it was well accepted. People actually like this model. It made a lot of sense because, they really didn't have any other option though. So they thought, yes, this is it. This is the plum pudding model. Atoms এরকম দেখতে, একটা বলের মতন দেখতে. It's permeable. Permeable means like things can go through it, and the thing is positively charged, and the particles floating inside electrons are negatively charged, right? Now then came the problem. Problem হচ্ছে somebody decided to prove this correct, not prove this wrong, prove this right. So there were these two physicists, Geiger and Marsden. Okay, so Marsden. These were two physicists. They wanted to prove this model right. And they wanted to do experiment and show, yes, the plum pudding model is accurate, right? So they figured out that because the pudding, right, the material that is the proton is permeable, ওদের prediction ছিল, if you pass anything through the pudding, right, it'll just go straight through, because that's what J.J. Thomson predicted, that it's permeable, so things will just, pass straight right through it, right? So they wanted to prove that, because, they also were fans of this model. They thought that this is the right way forward. So they just wanted to give more concrete backing to this particular theory, right? So ওরা ভাবছে যে if they fire particles at this nucleus, this atom here, they'll just go all straight through. And they just wanted to do that experimentally and prove it, right? So ওরা কি করছিল? What was their plan? So the experiment is something you need to be aware of. So আমাদের syllabus experiment নিয়ে বেশি question আসে. So the experiment went something like this. The person, Geiger and Marsden, right, they decided to take a gold foil, okay? So take a gold foil like that, and they wanted to fire particles at the gold foil. Now you have to understand, this is early 1900s, right? আমরা এখনো হচ্ছে electron, proton কে isolate করতে পারি না. So what did we use to fire at this gold foil, right? So what they did was they took a chamber. আমি একটা better version দিচ্ছি কিছুক্ষণ পরে, but আগে আমরা বেসিকটা দেখে নেই. They took a chamber that contained a radioactive element. So what's a radioactive element? It's an element that will undergo radioactive decay, and as it undergoes radioactive decay, it emits particles. That's the only way we could produce particles back in the day, okay? So the sample that we took was known for emitting alpha particles. So এখান থেকে যেটা বের হবে is a stream of alpha particles. So radioactive element is known for emitting alpha particles like that. So alpha particles will be coming out from here. How do we make them come out like this? It's part of our syllabus. And the prediction was that these alpha particles, right, would just go straight through. But here's the problem though. We can't see alpha particles. So how would we know that they went straight through? There has to be some way of figuring that out, right? So what did a course say? On the back end of this particular gold foil, right? Gold can we use course is also an important question. We'll come to that in a bit. But at piche, what they did was they set up a screen, and a screen like a barrier, like a thing where the particles will go and collide, right? So the screen is made up of this compound called zinc sulfate. So zinc sulfide, and zinc sulfide has this property, which is when particles collide with zinc sulfide, they make the zinc sulfide glow. Okay, so at the screen and we screen is coated with zinc sulfide. So the screen has like zinc sulfide coating on top of it, and this is your gold foil. This is the gold foil, and this is the alpha emitter here. And what they figured out was that তোমার যদি হচ্ছে এই alpha particles গুলো fire করা হয় towards the gold foil, right, ওরা straight যাবে এভাবে, and as they go straight towards the gold foil, what's going to happen is that they'll go straight through, because that's the structure of the atom that we know back then, right? That it's permeable. So the prediction chilo, they'll just go straight through. Our piche ekdom machkhane, you'll see some bright spots. So in machkhane, you'll see some bright spots show up. It'll basically light dilute, and then the light will reveal to you green color light hoy. The light will reveal to you the particles go straight যাচ্ছে. This was their expectation. Okay, so ওরা এটা expectation নিয়ে experiment start করে. So the screen আমি flat করে দেখাই, স্ক্রিনটার মধ্যে যেটা expectation ছিল যে স্ক্রিনটা পুরো খালি থাকবে, আর স্ক্রিনের একদম মাঝখানে একটা জায়গায় খুব high concentration of green light দেখা যাবে এই জায়গাটায়. Okay, ছোট এই জায়গাটায় green light দেখা যাবে এরকম করে, কেন? Because the particles are colliding here, and that confirms that even though gold is a solid material, the atoms are permeable. So what will happen is that the alpha particles will just go straight through, right? That was their prediction. And they did the experiment, and things were very different. So what happened was that when they did the experiment, eventually they found that yes, the particles at the center do glow. They do create like a very bright spot at the center, but there were some spots here as well, like that. So there's some spots showing up on the side. That didn't really make sense though, because it's a permeable thing, right? But it's empty. So ওরা ওটা ভিতরে গেলে সাইডে কেন চলে যাবে? So there are a lot of stories behind this, like, what they actually wrote in their paper. They said that imagine you're trying to throw a ball, right, into an open field in front of you, and you throw the ball and you see the ball move and come back at you, or go to the side and go to the side, because air to empty. Why would your ball like suddenly deflect to the left and right? Swing na kintu, it's like কিছু বাড়ি খেলে ফ্রেড চলে যাচ্ছে. So that's when they started wondering, wait, what happened here? Because যেটা দেখছে ওরা particles গুলো যে এভাবে চলে যাচ্ছে, গোল ফয়েলটাকে ক্রস করার পরে they go and hit the sides like that. So এটা তো হওয়া উচিত না, because there's nothing there inside the atom that can do this to an alpha particle. So that was the first confusion they had. But there was a bigger confusion, a way bigger confusion. This confusion is that when they put a screen on the backside, ulta dige, they place a screen here, right? They found that this screen also shows bright spots. So jeta notice korche that the screen at the back, like ei je piche je screen ta, ekheneও somehow bright spots showed up, like here, there, right? So that means that the particle collided and came back somehow. That is more baffling for the physicist. Okay, deflection hote pare, maybe electric field or something, কিছু একটা deflection hote pare, but how would it come back? Now the thing is that you might not understand the gravity of what they actually saw, because এখন তো you know what the atom looks like, right? But ওদের যেমন একটা point ছিল, is like you fire a bullet and the bullet comes back at you, but there's nothing in front of you, the bullet just comes back at you. That was their feeling, like what happened? Why is the bullet coming back? What did it collide with, right? And they were stuck here. They were stuck here for a few years because they found that 95% of the particles should have it. That's no problem. 95% of the particles, right? Around 2 to 3%, a 2% দিলাম, or 3%. 3% হচ্ছে এই যে সাইড গুলোতে যায় এরকম করে, right? And this 1% or less than 1% in some cases, right, comes back. So the question was that, what is this like outcome? Prothome they gave it to the reasoning behind uncertainties, the approach, experimental setup error, on kichur upore je this could be the reason, right? But when this experiment was replicated like thousands of times, literally, right, everyone had the same outcome. Statistically, the outcome was exactly same. Okay, so that's when confusion was that the model of the atom that we know is not really right. Our model would only give us one outcome. তোমরা কি আমাকে বলতে পারবা, if the J.J. Thomson model or the plum pudding model was correct, right, how would the screen look like if it was correct? Ki notice korte screen e? Yes, you'll find the center here is just super bright and there's absolutely nothing on the side, just one center circle, perfectly bright. Kichu nai side ekdom, not even by mistake, right? But ekhane jeta dekha jacche scattered, like they're going left and right somehow. And that's when this physicist from New Zealand, Ernest Rutherford, theoretical physicist, right, looked at the data and then he came up with an idea. He was basically inspired by something. So he said that, wait a second, if that's the case, right, maybe we should rethink the atom. So he said that the atom consists of protons, right, which are positively charged, and these protons are all clumped up together at the center, not one big chunk, but rather small pieces that clump up together at the center like that. And he called this, he was the first person to give the name, he called it the nucleus. He said the nucleus of the atom is where all these particles are, stacked together. Okay, so you can have a stacked kora. But then people said that, well, what about the electrons? Where are the electrons? He said that the electrons were actually not in the like this place. They were in an area around the atom. So he said that the electrons were like, floating around. like this, and he said that the electrons were just hanging around the nucleus like that. But that's when the very important question came along, that previously the electrons were inside the proton, if you remember the plum pudding model, right? Taken to the electrons are outside. And if your protons are at the center, the protons must be positively charged, right? And the electrons are negatively charged. So wouldn't that mean that the protons and electrons will attract each other, and the electrons will then eventually go and like settle down on the body of the atom like that, right? But that doesn't happen. So what's keeping them from falling down? Do you guys remember what prevented them from falling down? The neutrons কিন্তু এখনো discover করা হয়নি, neutrons আরো অনেক পরে discover করা হয়. There's this Chadwick experiment that discovered neutrons. At this point, we didn't know that neutrons existed. So the question is, why aren't the electrons falling down? Shells তো হচ্ছে imagination. Shells বলতে তো কিছু actually নাই, because if you go and go down to the size of an atom, right? কি shell পাবো এখানে, like an egg shell? Or what shell? What is that shell you're looking for? Shell bole kichu nai to. Shell is just a name given to the place where the electrons move around. Right, a lot of you said electrostatic attraction. তাহলে তো আমার electrostatic attraction electrons গুলো সব এখানে এসে বসে থাকবে না? What are they doing out there? Right? So this should be the case. Attraction হচ্ছে, very good. You are right. Attraction হয়. And wouldn't this be the structure of an atom, right? But Rutherford said the atoms electrons are outside here in this outer region. Okay, so it is too complicated, but I remember mentioning this before. So our বুঝাই জিনিসটা. So Rutherford বললাম না, he took inspiration. People obviously asked him this question. Well, what are you talking about? Where are the electrons? How can they be just floating around, right? So he said his inspiration was the solar system, the planetary model. So back then, solar system matro properly bucha hoy. People were trying to incorporate the solar system into whatever they see around us. So he said that the electrons were moving around in orbits, and that's where the term orbitals came from. So he said that the electrons were in these pathways that were known as orbitals, and these pathways are yeah, so this is where the electrons are moving around, right? And he said that the electrons are not falling into the nucleus, right? Because they're moving. They're always moving. So we learn in A2, the first chapter, is that if you're undergoing circular motion, you never fall, and you keep going in circles. Exactly what's happening to the Earth around the sun. The Earth is supposed to crash into the sun, right? Why doesn't it crash into the sun? Because it's just fast enough that it doesn't crash and rather goes around in circles, right? So this is what the Rutherford model of the atom was. He said that a masculine জিনিসটা দেখা যাচ্ছে, that he coined the term nucleus. So this was the first time somebody used the term nucleus, probably inspired by the nucleus itself, I don't know. And the orbit of your atom, which is the place where the electrons are moving around. And this is known as Rutherford planetary model of the atom. Okay, this is the one we will use this. Turns out 2 years later, after this was discovered, it was proving wrong. This is of the model of that atom. Okay. But then one realized that the point was the wrong thing. And when we keep the wrong stuff, and then you go something like the previous one was wrong, right? So wrong is one part of the nucleus is perfect. The other four nucleus is like perfect, and that's why we learned this. But the electron data and the electron ecosystem right now, it's wrong. So the electron is not actually doing this. And it turns out what the electron does is so complicated, right? Even if you finish your A levels, you still don't know really what they're doing. And to be honest, people still don't know what they're doing. So it's not your fault. So the point I'm trying to make here is that we are not actually focused on the electron and its accuracy of its existence. We are more focused about the fact that the atom has a nucleus, and the nucleus has some words to describe it, very particular words. the nucleus is very small, extremely small. I'll explain soon how small. It is very massive. Now, you may feel that, well, that sounds like opposites. How can something be small and massive? In physics, massive has nothing to do with size. It has to do with mass. And yes, the nucleus is very heavy. Okay? And because it's small and massive, naturally, it is extremely dense. So the nucleus is small, massive, and dense. How small is a nucleus? Let's try to understand that. So to give you reference and context about what the size of a nucleus is, right? Football stadium would be the best way out there. So you have a football stadium here. This is your atom. Okay. How big is the nucleus here? So if you want to understand in terms of size, right? So is the nucleus the size of a football? Is the nucleus the size of the, center circle? Is the nucleus the size of a footballer's head? Is the nucleus the size of the footballer? How big is the nucleus? If the whole stadium is the atom. So if pura stadium ta jodi atom hoy, nucleus এর size টা কতটুকু হওয়ার কথা? So it turns out the nucleus, right, কাছাকাছি গেছে অনেকে, is the size of the coin used by the referee for your kickoff. যে কয়েনটা থাকে ওই কয়েনটার size. So it turns out that the coin at the center of the football field, right, is actually the size of the nucleus, whereas the whole football field is the atom out there. So the question is, if the whole football field is the atom, but the mass is all in the nucleus and the coin, right? So the coin data atom horror kotha. So it turns out it's not, because the electrons occupy this whole football field. So when you look at the electrons of the atom, you'll find that they're everywhere in the football field at different places. So different jaga football field, you'll find the electron moving around. So therefore, atom to just not the nucleus, it's the protons and the electrons, right? So once you see the protons and the electrons together, you'll find that the atom is the size of a football field. But if you look at the nucleus, that's the size of a coin at the center. But here's a strikingly, shocking piece of information. That coin that's at the center weighs the same as the entire football field, because the nucleus contains 99.99999% the weight of an atom, even more. So therefore, the whole weight of the stadium is in that coin there. And that's why they're the most dense material in the universe, full stop. There's nothing comparable. Okay. So the idea is that your nucleus, right, is so dense, right? To give you context, imagine kora khub difficult. I mean, density itself is very difficult to imagine. On top of that, etar density koto beshi imagine korte gele, we'll have to think of in a more creative way. So the thing they say is that you take a spoonful of nucleus. So I make a spoon nilam, choto tablespoon. Okay, so tablespoon, a teaspoon. This is a teaspoon, right? And I fill it up with nuclei, protons, nucleus. It is filled with nucleus here, right? A tablespoon of nucleus. How much will it weigh? Was something somebody wondered for some reason. I don't know why, but thankfully we now have a number. So if you take a teaspoon or a tablespoon of nucleus, right, the weight or the mass of this would be similar to the Himalayan mountain range. So all the mountains in the Himalayas, right, oi shob mountain ja weight, like a teaspoon of nucleus will actually have the same weight. Achha? To give you more easier reference, heavier than Bangladesh. Okay, just imagine this teaspoon is heavier than Bangladesh, because it's so dense. That's the thing. The nucleus is extremely dense out there, the most dense material in the universe. It can lead to the formation of black holes and neutron stars collapsing and gravity becoming infinite because of these particles out there, right? So my question is, you are made up of nucleus, right? Why aren't you popping into a black hole? Or why don't you have like planets and moons going around you? Tomorrow to onek dense mass, and you're supposed to have a very strong gravity, right? So keno eta hocche na? Why is your density so low that you almost float on water, right? but whereas you're made up of nucleus. So can you tell me the reason behind this? Yes, very good. You're not made up of nucleus, you're made of atoms, and atoms are very low density because they're very far apart. As you can see, you're not made up of the coin. What are you made up of? You're made up of football stadiums. So your body is like this. একটা football stadium, পাশে একটা football stadium, right? So if you look at that, if I want to find the density of this structure, right? I mean, density কেমনে বের করব? Mass by volume, right? Mass হবে, yes, all the mass of the coins, but it's a massive at the volume. So once you do that mass by volume, it turns out to be just a normal density out there. Okay. So yes, if you were made up of neutrons, right, definitely you'd have your planetary system right now, but you're not. So therefore, what happens is that you're just the same density as clay, water, and I don't know, tomato. Right. So yeah, that's actually a very good point. All of Bangladesh's atom have less than a teaspoon of nuclei. Absolutely right. So if you take a teaspoon, if you take all the atoms in Bangladesh and extract their nuclei, right, they'll fit into a teaspoon. That's actually a very good observation. So yeah, that's true. Right. So এটা হচ্ছে the atomic structure. এখন আমাদের যেটা করতে হবে, we're done with the core part. তোমাদেরকে হচ্ছে syllabus requirement অনুযায়ী কি লাগবে ওগুলো একটু শিখে তোমাদেরকে, like as in what are you expected to be able to answer from this topic. So আমাদের এখানে এক্সপেরিমেন্টের উপর ফোকাস বেশি, মানে যে এক্সপেরিমেন্টটা করা হয়েছে এখানে এক্সপেরিমেন্টটা অ্যাকচুয়ালি কিরকম দেখতে এটা তোমাদেরকে এখন দেখাবো, এরকম দেখতে না, it's more technical. So we'll look into the experiment and yeah, I'll give you notes on this later on. But isn't the nucleus inside atom? হ্যাঁ, that's the thing. মানে আমি তোমাদেরকে সিম্পল একটা এক্সাম্পল দিই, তোমরা যদি ম্যাথ করতে চাও করে দেখতে পারো। This is nucleus, okay? এটার মাস হচ্ছে 1 into 10 to the power minus 21 kilogram, okay? আর এটার ভলিউম হচ্ছে 1 into 10 to the power minus 40 meter cube. Right, so here to quick math করে বলবো, what is the density here? এটা nucleus একটা, just quick math. What's the density? I'm making up some numbers here বোঝানোর জন্য, আমি তাও নিউক্লিয়াস অরিজিনাল ডেন্সিটি দেখিনি। এরকমই হয় 10 to the power 18 19, তোমাদের কত আসছে এখানে? আচ্ছা ঠিক আছে, ওকে, কাছাকাছি। সো 1 into 10 to the power 19 kg per meter cube, মানে 1 meter cube of this nucleus will weigh 1 into 10 to the power 19. That's crazy, the amount of mass you have here. It's heavier than the earth. 6 into 10 to the 24, almost the mass of the earth, in fact. Okay, but here's the thing, in nucleus তোমার body ভিতরে, why aren't you so heavy and dense? Because atomer কি হবে? So if I look into the atom, যেটা একদম মাঝখানে nucleus exist করে, right? So that's right there. What is the mass of the atom? Same, 1 into 10 to the power minus 21 kilogram. But what's the volume of an atom? The volume of an atom is 1 into 10 to the power minus 21 meter cube. Can you tell me what's the density of the atom? Yeah, so এটা actually আর ছোট হবে, I mean mistake here, 24 হবে। হ্যাঁ, 24 হলে কত আসে? That's the exact value. 1000 এর কাছাকাছি আসার কথা মনে হয়। 1000 আসে না? Yeah, 1000. So 1000 kg per meter cube. Same mass কিন্তু দেখো, mass same. But problem কি হচ্ছে, the atom is massive in size, and when the atom is massive in size compared to the nucleus, density naturally fall করে, and you have a density of 1000 kg per meter cube, which happens to be the density of a person, because we're very similar density to water. তোমরা কি লজিকটা বুঝছো? Couple of you asked me this question. এখন কি clear that yes, we are made up of nucleus, but we are not made up of only nucleus. We are made up of atoms actually, which contain the nucleus. And when you see an atom, that's very big in size, and because it's very big in size, we mass to spread over a larger area, and that's the reason why you have a low density. আচ্ছা, anyways, এই পার্টটা অত I don't think is that important. তাও যদি প্রবলেম হয় আমাকে বলো, I'll explain again ক্লাসে, but আজকে যেটা করতে হবে, we need to look into the experiment. Okay, so experiment to বুঝাই experimental observations and outcomes. Right, so what is this experiment? This is the Rutherford alpha scattering experiment. Rutherford alpha scattering experiment. এটা নিয়ে কোয়েশ্চন বেশি আসে। Rutherford alpha scattering experiment. What is this Rutherford alpha scattering experiment? It's the one that Geiger and Marsden did. Okay, no, people don't really remember their names, that's why I keep telling their names. They were the original people to do this. Okay, Rutherford takes the claim to it, but that's because he eventually found out what's going on. But it's actually Geiger and Marsden set up. Yeah, it's the same as your O level, but এখানে আমাদের হচ্ছে a couple of things extra add করতে হবে. Okay, extra add করতে হবে মানে আমি O levels actually করাই ফেলছি. So if you have done your O levels with me, you'll find that it's exactly the same. আচ্ছা, আমি জিনিসটা বুঝাই। I do that in O levels so that আমার A levels I can do this in like one class. এর জন্য O levels set to extra করে রাখি। So আশা করি you won't have much trouble here. So the setup goes something like this. You have this chamber, right? And this chamber has, let me fix it just a second. Right, this is the chamber here. And the chamber is a vacuum. Question জিজ্ঞেস করতে পারে, why a vacuum? Why do you need to have a vacuum here? কি answer কে বলতে পারবা? কেন vacuum use করা হয়? Right, so that the alpha particles are not deflected by surrounding particles. মানে পাশে particles গুলো থেকে bother না করে, okay? So it's a vacuum. And মাঝখানে we place our thin gold foil. It'll be highly appreciated if somebody can remind me why thin gold foil. কারো কি মনে আছে এটা? So the term that's used here is that it's gold foil, obviously, but it's a particular type of gold foil. It's a very thin gold foil. Why a thin gold foil? Oh, that's pretty good. A lot of you remembered that. Acha, okay. Some of you don't, but most of you do. Okay, perfect. So আমি ওটা এক্সপ্লেইন করছি, যারা বুঝো নাই কেন, এটা I'll explain soon. So thin gold foil হচ্ছে এটা থাকে এখানে, and এখানে একটা চেম্বার থাকে যেটা ভিতরে we have our alpha emitting radioactive material. Uranium 235 use করতো, but I have seen some other places যে অন্য elements use করা যায় as long as they are emitting alpha radiation. Okay, so sorry, uranium to orange, yellow. Right, so you have your uranium there, and the uranium will undergo radioactive decay and it'll emit alpha particles. Can you tell me which way does it emit alpha particles? A uranium sample, does it emit up, down, left, right, forward, backward? Right, it goes everywhere. It's going everywhere, which is a problem, because what if it just straight goes like that and we're like wondering, oh, something's wrong with the atom, but it just started off like that, right? So this is a problem. This is a big problem, because what if we were wrong and we just realized, wait a second, alpha particles also randomly বের হচ্ছে. Maybe that's why we see the deflection. Why would they all go in a straight line, right? So of course they had to fix that. So that's something you need to learn. So to prevent this problem, right, they came up with a solution which was right in the front of the chamber that you see here. They placed a structure যেটা আমরা A2 থেকে অনেক ইউজ করি, অনেক না মানে ইউজ করতে হয়. It's called a lead. Do you know what the name was? Collimator. Collimator. Lead collimator is basically a filter made up of lead. So যেটা হয় এখানে, yes, alpha particles will do their thing. They'll undergo radioactive decay. They'll move left and right, up and down. সব দিকে যাবে. But the lead collimator has these very small gaps that are parallel to each other, which means only the alpha particles that are straight can pass through. The alpha particles that are at an angle will fail to pass through. So it turns out eventually alpha particles যেগুলা সোজা বের হয় খালি ওরাই যেতে পারে, and therefore you don't have that worry যে wait alpha particle maybe নিজে থেকে শুরু থেকে bend হয়ে বের হয়েছিল. That is not likely. Okay, so yeah, this is what happens here. And তোমাদের হচ্ছে, I think you guys remember that the screen is coated with zinc sulfide. So this screen being coated with zinc sulfide means এই জায়গাটাতে হচ্ছে bright spot দেখা যায়. Do you guys remember the term used to explain the bright spot? They had a name, a bright জিনিসগুলো. What do you call them? Yes, very good. Scintillation. Scintillating থেকে. Okay, so these are called scintillations. A scintillations হচ্ছে like small sparks, and the sparks are like small thunderbolts or lightning. And then you look at those and you get an idea যে এখানে particles বাড়ি খাচ্ছে. Okay. Right, so that's what was expected. However, as we know the story goes, the particles went this way, that way, that way, this way, and that way. These are referred as small deflections. Okay, so low angle deflections or small angle deflections. So there are plenty of small angle deflections taking place here, and that 1 in 100 million, right, goes fully back, and that's referred as a large angle deflection. So this is what it looks like. So once again, I'll label the parts here. এটাকে বলা হয় lead collimator. Why did it deflect? We'll see right now. Why did it deflect? Lead collimator. This is the alpha source. তারপর হচ্ছে what else is going on here? Vacuum, gold foil, zinc sulfide coating. Zinc sulfide coating. Right. So that's the experimental setup. Now the question is, why? Why did they do this? Why did they have small angle deflections and large angle deflections, right? So we'll have to go down to the atomic level and imagine, right? You have a layer of gold atoms, right? These are gold atoms here. A layer of the single layer. Right. So these are gold atoms there. They're all stacked next to each other because gold is solid, so they barely have any molecular spacing. All next to each other, they're very tightly packed, and they all have a nucleus. Right. So nucleus. They can A level So if you have a class of this, so when we fire alpha particles, we find that most of them will just go straight through because they're far away from the nucleus. By the way, do you guys remember what charge alpha particles were? Charge কি ছিল? Yes, positive plus 2 impact, right? So you have your particles going like this and that. Like that. So most of them are going straight through, right? So terrible. However, as the particle starts to come close to the nucleus, right? The nucleus is positive according to Rutherford because it's made up of protons, right? your alpha particle is also positive. As a consequence, the alpha particle experiences repulsion, and the repulsion gives a force, and that makes this thing deflect slightly. And the problem is that the closer you get, right, the force is greater and the deflection is more prominent. And as a result, what we find is that there are these deflections showing up here. And deflections গুলো যত কাছে থাকবা তত বেশি হবে। এই যে, that's how it looks like, right? So the closer you are, the stronger the deflections are, right? Now, turns out nucleus is really small. So once in a, not even a blue moon, once in a millennium, in terms of time factor, this one will hit the nucleus. And the nucleus of gold is pretty heavy because it's plus 79, maybe I forgot the gold proton number, 79 so which is very heavy compared to alpha, which is only 4, right? So the alpha particle it's like hitting a truck. It just goes back. And that's that very small chance of colliding with the nucleus that can make this happen. And this is what your deflection reason is. So deflection takes place because the nucleus is positive and your alpha particles are also positive, and they get really close to each other and they repel each other. And because they repel each other, they start to move apart, as I have shown. Okay, so asha kori tomra buchcho logic technique ki hocche. But the point I'm trying to make here is that deflection gulo hoy because of the positive charge, small angle deflection. Are large angle deflection ki positive charge er jonno hoy, or is it for something else? What do you guys think? Can you tell me large angle deflection ta kisher jonno hoy? So the small deflection, there's a small deflection. They happen because of repulsion, because of positive or repulsion. But what about the large deflection? Yes, the large deflection takes place because of colliding. So collision takes place. Okay, so yeah, that's the reason why the outcome looks like this. Now, if you use statistics, right, you'll get an idea that why the nucleus is so small. So let me give you a simple analogy here. Imagine you have a wall in front of you, okay? Are a wall model? There's a hidden pin somewhere. Pin rakha. So ওই pinta কোথায় আমি জানি না, but I have been provided with infinite number of water balloons. So I have these water balloons here. A water balloons গুলো আমার কাছে দেওয়া, and আমাকে বলছে that find where the pin is using the water balloon. তোমরা কি আমাকে বলতে পারবা what can I do with the water balloon to find the pin on the wall? এই ওয়ালের মধ্যে একটা পিন আছে কোনো এক জায়গায়, right? So how do I find the pin? Yes, I'll throw. So I mean, water balloon গুলোকে নিয়ে কি করব? I'll just randomly start throwing at the wall. So I'm throwing at the wall, throwing at the wall. Water balloon গুলো ফুটে না. Throwing at the wall, throwing at the wall, and water balloon গুলো অনেক ছোট, let's say. So I keep throwing at them, হচ্ছে না. But then after a million throws, right? Suddenly it pops. এই যে এখানে পিনটা ছিল। So এই যে এই জায়গায় এসে বাড়ি খেলো and it pops, right? So can you tell me what's the size of the pin compared to the size of the wall? Is it very small or is it very big? Because it took me a million tries to hit it. Very small, right? It's probability. Probability তোমরা যদি করে থাকো math, you'll know this very well. এটার area যদি হয় 10 meters square, right? And probability is 1 in a million, the probability of impact, right? তাহলে কিন্তু you can do the math and figure out what the size of the pin is. Probability use করে. Okay? So if you don't have probability, don't worry. Basically, my point is the pin is very small. Otherwise, আমার যদি pinটা এত বড় হতো, let's say you have a pin here that's like this big. A Kenny wall মধ্যে you have a pin that's that big in size. Do you think it'll be a struggle for us to hit that? No, maybe 100 tries definitely hit করবা, maybe আর একটু বেশি লাগতে পারে, আর কমও লাগতে পারে. But when your pin is like microscopic level, like there, right? Wouldn't you require a lot of tries? There, that's the pin, right? Wouldn't you require a lot of tries before you can successfully hit that? Exactly same জিনিসটা এখানে হচ্ছে. when we fire the alpha particles at the nucleus, right? 99.999% just go straight through, deflect korok na korok, but they just go straight through. This 1 in a million, 1 in a billion, 1 in a trillion, right, comes back. That tells us what? That nucleus, which sent it back, must be really small in size. One of you asked the question, what if the nucleus is positive and alpha particle positive? Would they collide? And they do collide. You know why they collide? Because the alpha particle has enough energy to move and go and overcome the repulsion. So alpha particle turning high velocity to jet. Right. So this is it. I want to share something. A level, so there's this issue, a topic here. Wait, I'm just to share quickly, then I'll start the next part of our chapter. So A level, যেটা বলে ওরা ওইটা হচ্ছে Rutherford actually never confirmed that the nucleus was positive. So this is the answer to everything that I discussed today. But আমি যা আজকে বলছি সব এখানে লেখা আছে. But Rutherford actually never knew that the nucleus was positive. He said the nucleus was charged because experimentally positive proof করার কোনো way ছিল না. He said the nucleus was charged. And তোমাদেরকে মাঝে মাঝে question করতে পারে যে why would a nucleus that's negative also give the same outcome? মানে আমার nucleus যদি negative হতো, just saying কোনো কারণে outcome same হতো. Can you tell me why? Now, why would the outcome be same if the nucleus is negative? কেউ কি বলতে পারবে এটা? জিজ্ঞেস করতে পারে, এটা এক্সেলে করে তো, কেমব্রিজে আই হ্যাভ সিন এমসিকিউজ এ অপশনগুলো একটু অড থাকে. সো why is it possible that the nucleus could have been negative as well? Nah, it's because I'll tell you why. না না ওই তোমরা ফিলোসফিক্যাল লেভেলে চলে যাচ্ছ that we assume the universe to have a plus and minus. ওইটা চাচ্ছি না. I'm just asking, like, it can also be negative and then the answer and the outcome would still be fine. I'll tell you why. So আমার যদি পজিটিভ পার্টিকেল আসে কি করবে? রিপেল করে দূরে সরে যাবে. Can you tell me নেগেটিভ পার্টিকেল আসলে কি করবে? Yes, it'll go that way. ডিফ্লেক্ট করে এদিকে চলে যাবে, মানে মিস করে উল্টা দিকে চলে যাবে. সো দ্য যেভাবে এসে এভাবে চলে যাবে যদি অ্যাট্রাক্ট হয়, আর এভাবে করে এভাবে চলে যায়, রিপল হয়. সো দ্য পয়েন্ট আই এম ট্রাইং টু মেক হিয়ার ইজ দ্যাট there's going to be deflection, and এটা পজিটিভ বা নেগেটিভ যদি হয়, ডিফ্লেকশন ইজ গোনা বি দ্য সেম. ইয়েস, একটা উপরের দিকে হবে, একটা নিচের দিকে হবে, বাট আমাদের তো কোনো আইডিয়া নেই বুঝার কোনটা প্লাস মাইনাসের জন্য. সো রাদারফোর্ড originally in his paper stated that the nucleus is charged, but then some other physicists did the math and they found out that the charge can only be of protons. So the protons are positive, therefore the nucleus has to be positive. So experimentally কিন্তু positive proof করা হয় নাই. That's what I'm trying to say. Okay, experimentally proof করা হয় the nucleus is charged. So আমি এখানে অ্যাড করে দিচ্ছি এটা. Yeah, I'll give you like a 1 minute break. Positively charged. So originally was thought to be either plus or minus. Okay, 5:08 baje. 5 আচ্ছা একটু বেশি দে, 5:10 এ ব্যাক করো. So 2 minutes break. I'll start alpha beta gamma next. All right, so let's start. We're done with the checklist করে নি কি কি হয়ে গেছে এখানে I think 1 2 3 4 5 6 11 আচ্ছা 5 পর্যন্ত হয়েছে we will move on to some page here that will wrap up 4 of them together page 124 right page 124 বের করো page 124 Right, so the atomic notation. Let's see what the atomic notation is. Atomic notation হচ্ছে super easy একটা জিনিস that when you have the name of an atom, there's a standard of noting this down. So standard is just the name of the atom, right? Whatever the alphabet is given to it. এখানে একটা নাম্বার যাবে, এখানে একটা নাম্বার যাবে, এখানে একটা নাম্বার যাবে, আর এখানে মাঝে মাঝে একটা নাম্বার থাকতে পারে যেটা আমরা সবসময় দেই না। So my question for you is, can anyone tell me what is the number that goes here at the bottom? এখানে কি লিখি আমরা? What is the number that goes here? Yeah, it is the physics say it is the proton number, or you can also call it the atomic number. Okay, physics atomic number to use kora hoy na, but it's also referred as the atomic number. So atomic number bole kono problem nai. Atomic number, right? Can you tell me what's the number up here? What do we call this? Right, it is called the mass number. Right, it's also called a nucleon number, correct? What goes there? Yeah, this is the charge. And what goes there? মাঝখানে? Right, neutron number, correct. Right, so this is the atomic location. Now, it is possible that this may have happened, and I know you know this as well, that there's an X, right, whose numbers look something like this. J, 12, 6, 12. Our element, right? That looks something like this, which is 6 and 14. Can you tell me what are these? Right. They're all isotopes. So isotopes are elements of the same proton number, right? But different mass or nucleon number, or because they have different neutron number, to be honest. Okay. So if you look at the neutron number, then you get a picture of what's actually different about them. It is 6 right? For this, I can 8. Right, so these are called isotopes. Isotopes are কি same থাকে আর কি different থাকে আমাকে বলতে পারবা? Like two isotopes, right? What's same about them and what's different about them? No, I'm asking in terms of no. তোমার অন্যদিকে চলে যাচ্ছে. Sorry, I should have rephrased it. Not in terms of structure, in terms of properties. Like property wise কি different ওদের? Right, so they have same chemical properties. So if you look at their chemical properties, they're exactly the same. However, what's different about them? Physical properties. Mass তো তোমার ইচ্ছা, তুমি যদি mass নিতে চাও. So different হচ্ছে density, melting point, boiling point, conductivity, sorry, boiling point, এই জিনিসগুলো এগুলো বলে physical attributes. Okay, so different হচ্ছে physical attributes গুলো আর হচ্ছে same হচ্ছে chemical attributes গুলো. So when you have carbon 12 and carbon 14 in your body, right, you wouldn't be able to know any difference. Your body will function exactly the same way because they react exactly the same way. Right, so this is the atomic notation. এখানে ওরকম কিছু আর নাই আমাদের দেখার মতো. So আমরা যেটা এখন করব ওটা হচ্ছে এটা তো আশা করি বুঝছো তোমরা এখানে I think grade 8 এর জিনিস এটা. So what's new here? Physics দেখি কিছু নাই new. আজকের ক্লাস তো বলছে it's going to be entirely revision of all levels. This one is the alpha beta gamma part. Okay, so atomic stability. We do not have radioactive calculations in A2, okay? মানে half life calculation এগুলো কিছু নাই আমাদের. Just give me a minute. All right, so just screen it echo. Let me explain what's going on here. So let's say we have some common elements out there, like carbon, nitrogen, then you have your oxygen, you have I don't know, whatever element that you like, chlorine, right? Can you tell me their mass number and proton number? মানে হচ্ছে mass number মানে হচ্ছে your nuclear number. So carbon হচ্ছে 12 and 6, nitrogen হচ্ছে 14 and 7, oxygen হচ্ছে 16 and 8. Does anyone know what is it for calcium? Right, it is 40 and 20. Chlorine to vary করে because you know there are isotope ratios out there. Let's take a random one, like let's say 17 and 35, 37 হয়. So you'll find a trend here. So it turns out after we discovered the atom and the nucleus, right, we realized there's a big problem in the nucleus. What's the big problem in the nucleus? That the nucleus is only made up of protons. That's what we thought. And when you put two protons next to each other, or six of them next to each other, like how it's in carbon, right, it leads to a very big problem. Problem হচ্ছে, this nucleus that you see here is actually not going to exist. The reason behind that is these protons that you see here, they're going to repel each other. And they're going to repel each other with probably arguably the biggest repulsive forces in the universe. Why is that so? Because these particles are literally next to each other. But if next to each other had a number, that's what protons would be, like literally next to each other. Their values of separation is the smallest in the universe. So they will experience a lot of repulsion out there, and the nucleus will not exist. It will just fly off. The protons will fly off, right? But it does exist. And then we realize why they exist. So the reason why the nucleus exists and it doesn't like fly off and break down is because the nucleus also contains other particles. And one particle in particular, the neutron. So the neutron in the nucleus, right, comes and binds itself with the protons and glues them together. And these apply this force called the strong nuclear force. And that makes your nucleus extremely stable because every proton and every neutron are actually bound to each other by the strongest force in the universe. It not mean the strong nuclear force. It has to be the strongest force out there, right? এটা হচ্ছে ভিতরে একটা particular bond generate করা হয়, exchange particles বলা হয়, and this is the strong nuclear force example. Strong nuclear force. Now the thing is, a strong nuclear force can only be exerted and experienced between a proton and a neutron. Okay, and that's why the nucleus remains stable. So if you look at the number of protons and neutrons, you'll see that for every proton, you need a neutron to be stable, right? And you'll notice this reflection here. Reflection that you'll find that the number of protons and number of neutrons are similar. Ekdom same হওয়া লাগে না, but similar for all the elements here. So if you look at all the elements here, you'll find a number of protons and number of neutrons similar. So just 6 এখানে, 7 এখানে, 8 এখানে, 20 এখানে, 18 এখানে. So what does that mean? Every proton has a neutron to keep it in its place, and they create this very perfect harmonic system, right? And they're very stable. And that's the nuclear stability of a nucleus. But then something happens. You end up with elements that are uranium-like. So uranium is an element in the periodic table, right? And it has 92 protons and 235 mass numbers. So the number of neutrons it contains is 143. So this contains 143 neutrons out there. Why is that a problem? More neutrons means more stability, right? That's what we thought until we realized that the protons and neutrons bind with each other when they're right next to each other. So the strong nuclear force has a catch. It only works with adjacent particles, next particle. It doesn't work when it's further away, far away, and out of reach of a proton. So what happens is, I'm just draw this, it's stable because for every proton I've drawn a neutron, right? But what if I keep adding neutrons here, like how it's in uranium? That I keep adding neutrons here, more and more neutrons, more and more neutrons, right? Way more neutrons than I have protons. Problem ki hoye jacche, at one point these neutrons are so far away from a proton that there's nothing to keep them in their place. They become like extra fat. They need to leave, or they have to be gotten rid of. So these protons that you see here, they're binding to all the neutrons around it, right? But this group of this group of neutrons, ওদের কিন্তু কোনো bind করার scope নেই, like these out here. So what happens is they are looking for a way to escape, and ওরা escape করলে কি হবে? Nucleus start to stable হয়ে যাবে. Unfortunately, you can't make a nucleus just escape, মানে neutron escape, কারণ neutron একা একা থাকতে পারে না. It has to be with something, right? So these are the extra neutrons out there. So how do we get rid of them? Extra neutrons. So তোমাদের কি মনে আছে how you got rid of them? Right. So what happens is that this nucleus will undergo something called the radioactive decay. Radioactive decay. And during the radioactive decay process, what will happen is the neutron will escape. But the neutron will escape, taking away 2 protons with it. And this thing that escapes is referred as an alpha particle, 4 2 plus 2. And that is how the nucleus becomes a little more stable. Does it become stable right away? Absolutely not. Does it become more stable? Yes, it does, right? And this is what we refer as an alpha decay. So alpha decay is when your nucleus has extra neutrons in it and it needs to get rid of them, but the neutrons won't go away alone. So they go away with protons with them and they form an alpha particle. By the way, alpha particle only stable. So therefore, they do form a stable particle as they leave. This process is called radioactive decay. In our syllabus, we have 3 decays that we need to know. So the first one that we saw here, this is called the alpha decay. An alpha particle generate করা হচ্ছে। তারপর next আসতেছে তোমাদের, this is alpha decay, okay? The next one is called the beta decay. So beta decay ta ki ekটু দেখি আমরা। So beta decay is when your particle has or your atom has extra neutrons in it, but it's really small in size. Let me give you an example. So imagine we have nitrogen isotope with 16 particles in total. This is unstable. কেন? কারণ 7 এর জায়গায় 14 হওয়ার কথা। So if I draw the nucleus here, right? So I'll draw the nucleus here. This is 7. কয়টা হলো এখানে? 6, 1 2 3 4 5 6 and 7. Just a second, আচ্ছা আমি এটাকে ফিক্স করি। 1 2 3 4 5 6 আর একটা লাগবে 7 protons and 9 neutrons, right? 9. Right, so যে এখানে হচ্ছে তোমার নাম্বারটা হচ্ছে 9. So it's unstable. How does it become stable? So it becomes stable through a process known as beta decay. কি হয় beta decay তে? What happens is somehow from somewhere this particle called a beta particle, right, shows up, and this beta particle is 0 and -1, and it forms this element here. Can you tell me what's the composition of this element here? যেটা ফর্ম হচ্ছে এখানে নাম্বারগুলো একটু বলবা ব্যালেন্স করে। Right, it's going to be 16 at the top and 8 at the bottom, right? And that's the stable form of oxygen that's forming here, right? So this is called beta decay. What happened here? Let me explain. So if you look at the numbers, it'll actually reveal to you what happened. You'll notice that oxygen now has 8 neutrons, but it has more protons. So beta decay, the whole process, it's the process where a proton, right? A neutron breaks down into a proton plus an electron. It's a very unique interaction that takes place in the nucleus, but a neutron break down to a proton plus an electron here. And eta hoche is what beta decay is. And that electron that you see here, it's your beta particle. So this is a fast moving electron interaction that energy release, right? So fast moving electron is released here. Our alpha particle হচ্ছে এটা হচ্ছে helium nucleus. Helium nucleus. Right, so this is what happens. But A level session, there's a bit of a catch here. So 0 1 1 এটা হচ্ছে proton 1 sorry উল্টা লিখছি, এটা 0 হবে হচ্ছে, আর proton হচ্ছে 1 1 আর electron হচ্ছে তোমার 0 minus 1. So if you balance this, you'll find that তোমার balance হয়. Okay, so if you look at the number at the top, 1 1 niche 0, 1 minus 1 which is 0 হয়. But turns out there's another particle that shows up here. ওই পার্টিকেলটা হচ্ছে নতুন সিলেবাসে. It is very small particle and it's of no charge actually. It's this thing. It's called an anti-electron neutrino. You have to learn this. আচ্ছা, so এখন থেকে যখন হচ্ছে তোমার বিটা ডিকে শো করবা, you have to show that it also comes with an anti-electron neutrino electron eta. So eventually if you want to write this in words, কি হচ্ছে a beta decay is when a neutron, right, splits up into a proton plus an electron. And conservation law একটা আছে, we don't learn this in Cambridge but in Excel শিখতে হয়. ওই law অনুযায়ী there has to be another particle that shows up, and that particle is called an anti-electron neutrino. Now the deal here is that a anti-electron neutrino কি পুরো ডিটেইলস আমরা জানতে হবে. We learn about this in the topic that will be next, যেটা তোমাদেরকে টিউজডেতে করাবো. আচ্ছা, তার জন্য at the moment just একটু কি জেনে রাখো. It's called an antiparticle. আগে থেকে বলে রাখলাম, ওই antiparticleটা কি will learn next class. So yeah, that's the alpha decay, that's your beta decay. এখন আমাদের যেটা করতে হবে, the final one is something called a beta plus decay. All right, no, it has no charge. So the anti-electron neutrino is a neutral particle. We'll learn about this. Neutrinos ki শিখতে হবে. So neutrinos are neutral particle. They're very small in mass. They have no charge. That's why originally we didn't even detect them properly. But eventually we learned that these particles should be there every time emission takes place, right? So we can think of a very course that these particles do exist every time a electron is released in a beta decay. এটার একটা নাম আছে. I think I should refer to the proper name. Beta decay, beta some syllabus. So there's a beta decay, and I don't know. তোমাদের তো স্কুলে পড়া আছে. Do you know what beta decay is? This? Achha, anyways, it's called a beta minus decay. Beta minus decay. So there's a beta decay out there now. Beta plus decay and beta minus decay. So I'm going to do beta minus decay. We're going to do the beta plus decay next. So what's beta plus decay? So beta plus decay হচ্ছে kind of reverse of the process. Also down হচ্ছে এই টপিকটা তো নেক্সট ক্লাস করাবো সাথে করলে বেটার হবে, বাট আগে পড়ায় রাখি beta plus decay takes place when a proton absorbs a particle to form a neutron that are drawing through that. So that's a proton, 1 and 1, neutron, 1 and 0, plus it produces this particle here, which is an electron, but it's positively charged. So this is E1 and 0, plus another small particle, which is electron neutrino only. So beta decay টা হচ্ছে ওয়ার্ডে লিখি জিনিসটা. I know it may not seem like, you know, কি হচ্ছে বুঝতে একটু ডিফিকাল্ট হবে এখন, বাট এই পার্টিকেল গুলো কি আমি তোমাদেরকে যখন শিখাবো নেক্সট ক্লাস you'll have a better idea. But beta plus decay টা হচ্ছে a proton will become a neutron. So এটা এনার্জি লাগে অনেক for this to happen. plus it'll produce something called a positron, which is essentially a positively charged electron. Plus it'll produce what we saw earlier, an electron neutrino, antinar, electron neutrino. Right. So these are the 3 decays that we have in our syllabus. I'm going to check with the chat course in the Cura. No, that's it actually. Ionization ability, range, penetration, এগুলা নাই, এগুলা জিজ্ঞেস করেন ওরা। Right, so to checklist to দেখে আসি if I've covered everything or not. Actually the বাদ যেতে পারে, ওটা আমি next class এ করাবো because I think it's more appropriate with those topic. Infer the results of alpha scattering, done. Describe a simple model of an atom, done. Nucleon and proton number, yes. Isotopes, yes. Notation, done. Nucleon and charge conserved in nuclear processes. Yes, I think this is like the most basic foundation of the whole chapter. But the chemistry is based on that. You should know this. Describe the composition, mass, and charge of alpha, beta, and gamma. Yes, gamma is just electromagnetic radiation. And by the way, all level not the so nothing to worry there. But herbaceous, in fact. Understand that an antiparticle has the same, so it's a coordinator. Next class, state that electron neutrinos are produced in beta minus and electron neutrinos are produced in beta plus, antineutrinos in beta minus and neutrinos in beta plus. It's a course here, but I don't feel that কিছু বুঝছো তোমরা। So the next class যখন আমি তোমাকে neutrino শিখাবো তখন বুঝবা। Understand that alpha has discrete energies and beta has continuous range of energies because of এটা next class দেখাবো। Alpha beta decay equation, এটা পারবা তোমরা, very basic. Use the unified mass unit, এটা করাই নেই, এটা আমি next class এ করাবো। So yeah, that's basically it. 11.1 হয়ে গেছে। 8, 10 আর 12 টা actually করাই যেতে পারি, but I think হচ্ছে এটা এটার সাথে রিলেটেড, তো এখানে we learn about the antiparticles, so তার জন্য I think এইখানে বোঝানোটা easier হবে। And এটা একটা single table, next class এই টেবিলটা শিখালে you guys should be done with this topic. So yeah, my aim is Thursday question paper start kora, but Thursday I'll keep as a buffer for anything that I can't cover up within the next class. But yes, next Sunday we just start question paper and we keep doing question paper until your exam. Oh, by the way, একটা জিনিস বলে রাখি তোমাদের ওই book 1 or 2 তে হচ্ছে there are a lot of review questions out there. আমি ওগুলা করব আগে। Review questions গুলো খুব important, okay? Because you need to understand you know, chapter wise যে টপিক গুলোর কোয়েশ্চেন গুলো আছে ওগুলো পারতে হবে। I know a lot of you ask me এগুলার মার্ক স্কিম কোথায় কি কোথায়, আমি ক্লাসেই করব ওগুলা। So আমরা কোয়েশ্চেন পেপার করার মাঝখানে we'll do those review questions as well. All right, that's it. I'll stop the recording.
Recording stopped.
লাগবে না আমাদের। আমরা তাহলে হচ্ছে next class, which is on Tuesday, right? We'll do this fundamental particles, and that will be the end of the chapter and syllabus. Right, so আজকে এটুকুই থাকলো, আমরা বাকিটা কন্টিনিউ করবো।